Thermochemistry Chapter 2.0 2.4 Born-Haber Cycle. At the end of this lesson, students should be able to a. Define lattice energy and electron affinity. b. Explain the following effects on the magnitude of lattice energy. 1. Ionic charge. 2. Ionic radii. c. Construct Born-Haber cycle for simple ionic solids using energy cycle diagram and energy level diagram. d. Calculate enthalpy changes using Born-Haber cycle. Electron affinity, EA. Electron affinity, EA, is the heat change when 1 mole of gaseous atoms gains 1 mole of electrons to form 1 mole of gaseous ions. For example, the first electron affinity for oxygen is negative 142 kJ per mole. The second electron affinity is the energy absorbed when 1 mole of singly charged anions gain electrons to form 1 mole of doubly charged anions. The second electron affinity of oxygen is positive 844 kJ per mole. The second electron affinity is positive for any element because an electron is being added to a negative ion. There is a strong electrostatic repulsion and energy must be absorbed to overcome the electrostatic repulsion. Lattice energy. Lattice energy is the heat change when 1 mole of solid ionic compound is formed from its constituent gaseous ions. For example, heat released when 1 mole of sodium chloride compound formed from its gaseous ions is negative 771 kJ per mole. Lattice energy changes are large and the values are negative for the formation of crystalline solid because the formation of ionic bond is an exothermic reaction. The same amount of energy is absorbed when 1 mole of the solid ionic compound is completely separated into its gaseous ions. The lattice energy for lattice dissociation is energy required to completely separate 1 mole of a solid, ionic compound, into gaseous ions. For example, lattice energy for dissociation of 1 mole sodium chloride compound into its gaseous ions is positive 771 kJ per mole. The magnitude of lattice energy increases as the ionic charges increase, and the ionic radii decrease. There is a strong attraction between small ions and highly charged ions, so the magnitude of lattice energy is more negative. Magnitude of lattice energy for magnesium oxide is more negative than magnitude for sodium oxide because magnesium ion is smaller in size and has bigger charge than sodium ion, therefore, the lattice energy for magnesium oxide is larger than lattice energy of sodium oxide. What is dissolution of ionic solids? Dissolution is process by which a solid or liquid forms a solution in a solvent.
When an ionic compound, such as sodium chloride, is dissolved in water, strong dipole-dipole interactions between the ions and water molecules break down the cation-anion attractions in the crystal lattice. The energy change caused by this transformation is called the enthalpy of solution. Using Hess's law, we can divide this process into 2 successive steps. Breaking down all the cation-anion interactions in the crystal lattice and hydration of the resulting ions. The first step requires an input of energy equal to the lattice energy taken with the opposite sign. The process is endothermic, and so the enthalpy change is positive. The second step is exothermic and involves release of the hydration energy of the cations and anions. From the energy cycle, we can see that the enthalpy of solution is the difference between the enthalpy of hydration and the lattice energy.
Born-Haber cycle. The process of ionic bond formation occurs in few stages. At each stage, the enthalpy changes are considered. The Born-Haber cycle is often used to calculate the lattice energy of an ionic compound. Example: construct a Born-Haber cycle for sodium chloride and calculate its enthalpy of formation.
Let us use again our example of sodium chloride and try to calculate the standard enthalpy of formation of this compound.
We can see that the formation of sodium chloride can be broken down into several steps. Sodium is a solid metal under normal conditions. To form gaseous atomic sodium, the enthalpy of atomization must be absorbed. Now, the formation of sodium ions requires additional energy equal to the ionization energy. Chlorine is gaseous under normal conditions, but it is made up of diatomic molecules. Therefore, the formation of gaseous atomic chlorine requires the enthalpy of atomization. Because of the high electron affinity of chlorine, 349 kilojoules per mole of energy is released when electrons are added to produce chloride ions. If the resulting ions are combined together, they form a solid crystalline compound, and the lattice energy is released. We can see that the standard enthalpy of formation of sodium chloride is equal to the sum of all the energy released or absorbed at every step. Substituting the numerical values, we calculate that the standard enthalpy of formation for sodium chloride is minus 410 kilojoules per mole, quite close to the experimental value of minus 411 kilojoules per mole.
In previous lessons, you learned that if a reaction is considered in several steps, and the enthalpy of reaction is known for every step, the overall enthalpy change can be calculated using Hess's law.
Let's try with another example. Construct a Born-Haber cycle for calcium bromide, and find its enthalpy of atomization of calcium.
First, we consider the steps involved in the changing of sodium-calcium metal to gaseous calcium cations. The first step is the atomization of the metal, and we must find the enthalpy change for this step. Next, there is a two-step ionization of the calcium atoms to form first calcium plus 1 ions, then calcium plus 2 ions. The energy equal to the sum of the first and the second ionization energies is required for this step. Bromine is liquid under standard conditions and requires 31 kilojoules per mole of energy to vaporize. Bromine is composed of diatomic molecules in the vapor phase. Therefore, the formation of bromine atoms requires twice the standard enthalpy of atomization. When two bromine anions are formed, energy equivalent to twice the value of the electron affinity is released. Finally, the gaseous ions combine to form solid calcium bromide. Lattice energy is released. Because we know all the enthalpy changes except for the enthalpy of the atomization of calcium metal, we can calculate it in the following manner. The standard enthalpy of atomization for calcium is 178 kilojoules per mole.
Thank you for watching this video.